Okay, let's begin. Shh. You can do it. You can do it. Everybody on the internet. Hi. Look at everyone. Everybody showed up. All the keeners. The most people we've had in weeks, because it's the one before midterm. Interesting. Let's turn this way. Okay, so it's been a good week for you. So first, the labs get canceled because Kahina's absent, and now I got to cancel Friday's class because I won't be here. So you get just this, and as a result, we're actually cutting out some content. So today we're just going to talk about the midterm and go over what we've done so far in preparation for you writing the midterm, which will be, of course, as soon as you get back from reading week. Right, November 4, I think that is. Okay, so life gets easier and easier for you. How good is it to be you this week? Although I know you're sad. You're sad because you missed lab, and you're sad because you won't get to see me on Friday. That's okay. You can look at my picture online. So that's good. Okay, so the midterm, November 4. You know that. You all know that. Yeah, it's not a surprise. You know it's a midterm when you come back. Okay, and today we're going to look over what we learned, and we're going to look at the midterm. So I'll get to more details, but I will give you these two formulae in the exam sheet. But you're going to be given a cheat sheet. We'll talk about that in a second. And you can put anything else you want on there, but you don't have to put these two on unless you want to put them in your language, whatever that language might be. I'll give you whatever Z and or T tables needed for looking up things, if indeed you think you might want to look up things. But the tables will be there on the exam sheet as well, the relevant ones. The cheat sheet, sorry, not cheat sheet, resource document, reference companion. I don't know, because you're not cheating, so glad. So this is the first time I'm doing it for the midterm in this class, mostly because I forgot that I didn't do it in this class last time, and I said that I would, so I have to. So even though the exam is actually set up not for a cheat sheet, you get to bring one. Again, you'll be winning. It's just endless winning for you guys this semester. So yeah, you're going to have a cheat sheet, which is one single page, the size of a regular sheet, written on both sides, or one side, whatever you like. We can put anything you want on there. Anything you want. I don't care. If you think it'll help you, you can find some high-tech way to summarize the entire textbook on one page, like 3D printed, actually 4-dimensional modeling with microdots. Go crazy. Okay, but it's a waste of time because it's not going to help. It's not that relevant. So put whatever you want on the cheat sheet. It's okay. Right, so what's on the exam? It'll be all multiple choice because this is health sciences, and that's what we do. And there are going to be 70 questions total. It's a lot of questions, I know. But one is just a bonus. So it's actually out of 69, but if you get that bonus one, then you get that free. Okay? Because it's a tricky bonus one. And every year I give the same bonus question. You probably ask people what it is. And every year people have conniptions over the bonus question. They're like, sweat for 10 minutes in class. I don't get it. It's a bonus question. Let it go. Doesn't matter. Right? It's hard because it's a bonus question. Don't worry about it so much. So you could use math on 5 of them. You don't need to. Wink, hint, hint. What does that mean? You know, well, you'll see when you're at the test. So 5 of them at least you can work through without actually having to do any computations. 5 you actually have to do math on. And the breakdown is this: 2 probability questions, 2 bivariate analyses, and 1 t-test question. And the rest are all theory-based. What is theory? Is this true or false? The case of this, whatever it might be. So there it is. What will not be on the test? I will not be asking you to compute set scores. Aren't you happy about that? We won't do correlations because we haven't done correlations yet, really. Okay, we'll set the second half. We're not going to do independent samples t-test calculations because you don't know how to do that. You know how to do dependent and one sample only. And we aren't going to do ANOVA. Even though you learned that this past week, I don't think there's been enough time for you to absorb that stuff yet. So the ANOVA stuff will be on the final. So don't worry about studying about ANOVA things. So like I said, I'm going to give you the 2 formulas and the relevant table things, and I'll give you some scrap paper. What I usually do is the exam question sheet, there's like 3 additional pages in there you can have scrap paper. That you don't need because there's only like 5 to 10 questions. I need it. And there you go. Okay. What can you bring? Any kind of calculator you want. You got your high-tech graphing calculator. I don't care. You got a cheat sheet. Why do I care about the graphing calculator? Right. So anything you want. Not your phone though. That's if you can network it. That's pushing it. So no, none of that stuff. One for me, well, coffee, and your cheat sheet. Actually, well, one year I had a guy who exam starts and his calculator doesn't work. So he gets up and goes to the mall and buys a new calculator and comes back and finishes his exam. So that's hardcore. And today he's in an epidemiology program at U of T, so it worked out well for him. Interesting guy. He's actually a really successful male model also. So it's like, I know, right? Yeah. So like, yeah. I'm not saying. So he's like winning across all aspects of life. So okay. So what have we learned thus far? Yeah, there's actually a poster of him like over a highway in Serbia, apparently. Okay, what have we learned so far? We've learned. Any questions about the midterm, by the way? That's all I was going to say about the midterm, and now we're going to do just review. And we're really fast today. We'll be out of here probably in 15 minutes because there's not a whole lot to talk about. What a great week for you. You get things canceled, fast lectures. Okay, so interrupt me if you got any questions about the midterm as we go on. Because right now I'm just going to go over what we've learned throughout the year. Because you learn a lot. It doesn't seem that way to me. Based upon, no, I'm kidding. But you've learned a lot. So in the first lecture, we learned about the difference in different types of variables, most notably continuous versus categorical. And hopefully you in your head what that distinction is. As you go forward in your research careers, that distinction becomes increasingly important because the kinds of variables you have dictate the kinds of statistics and manipulations you can do. So we also call categorical variables discrete variables. We did a lot of time on levels of measurement. So nominal, ordinal, interval, and ratio. As I mentioned a few times, in practice we tend to confuse these two lumped together, but these two have to be distinct. So example of a nominal level measurement. Male, female, that's good. You can't rank them. Ordinal level measurement, example. Really? You guys are going to really suffer in this exam, really? Example of an ordinal level variable. Yes? Pain scale. No. No. For example, I can say on a scale of 1 to 10, how much pain are you feeling? I can say 1.5. Unless I just, you know what I mean? So, yeah. Exactly. So your rankings in the end of a contest or a race, number of rooms in a house, number of kids you have, that sort of thing. Interval ratio. What's the distinction between the two? Well, it's not absolute zero. It's a rational zero. Okay, there's a rational. So ratio has a rational zero, a real zero that corresponds to something in real life. Okay, and here, of course, is a table that I'm showing you already that summarizes all of the things relevant. Okay, we did some things on sampling, and again, this is a bit of wisdom that will come into play a lot as you move forward in your research career. So when we are sampling from a reference population to which ultimately we want to infer information. And we're selecting a sample from that reference population. And hopefully that sample is representative, which it usually is. We're not getting the extreme versions of that sample. If we are getting extreme versions, then we're on extreme ends of the dull curve. But I get ahead of myself. So we did descriptive stats versus inferential stats. So the difference between the two is descriptive stats is talking about my sample again, people in my class. Inferential stats attempts to infer information about the reference population from the descriptive stats. Okay, now what am I measuring in a descriptive scenario in a sample? What are the things I'm measuring called versus the things that I'm measuring in the reference? So if I measure your mean age, and I infer that about the mean age of the population, Courtney? That's correct. So my sample is a statistic, and in the population it's a parameter. Okay, pretty straightforward. Oh, there it is on that slide. It's almost like I knew that in the slides. Okay, so again, a statistic is about sample, and the parameter is about the reference population. And we've done these examples before. Ultimately, we want to use statistics to estimate parameters. Okay. In lecture 2, we looked at how we phrase research questions and why we phrase research questions and the difference between independent versus dependent variables. And the distinction, again, is the independent variable is free to be whatever it wants. The dependent variable varies according to the independent variable. So if I'm measuring the mean age between two different classes, you're free to be whatever class you want. So the class you're in is the independent variable. but the mean age per class depends upon which class you're in, so that's the dependent variable. Or in epidemiology, the independent variable is whether or not you smoke. You're free to smoke, but whether or not you get cancer, that's dependent on whether or not you smoke. All right, so here we go. All right. We did a little bit on defining variables, and traditionally this gives a lot of students intellectual problems. This year, no one's asked me about this. Strange. Every other year, it's always people who like sit me down for hours and try to get me to explain this in more depth. But this year, either you don't care, or you really get it right away. So I'm going to let you get it right away. But the important distinction here is that when you define a variable, there's a conceptual phase and an operational phase. The operational phase is when we actually get the variable, and that's what we do math on. We do our operations on this part. But ultimately, we're making conclusions about this part. So if I am trying to measure happiness, right, and I decide on a scale of 1 to 10, how happy are you, right? So suddenly that scale is the variable. I've operationalized the concept of happiness by applying a linear ordinal scale to it, or probably an interval scale to it, because I can go 1.5 happiness. Okay, so if I say all of a sudden my population's average happiness is 3.5 out of 10, does that tell me something? It tells me some things. It doesn't really get across the gist, the meat, the essence of happiness. It's just a number. So that's the intellectual-locity-ness thing of this distinction, is when we operationalize an idea, we lose a little bit of its magic. A scale of 1 to 10 isn't really happiness, it's a way of estimating happiness. So that's really what this slide's attempting to say very, very poorly, that I've now beaten to death, and I don't care enough anymore. Okay, so again, a conceptual definition is the theoretical meaning, and the operational definition is the precise set of conditions by which we define that meaning so that we can do things with it. Another example here is how long have you been on this planet? We say, how old are you? By years, which really doesn't get the same essence as the concept, but it's good enough. Then we moved on to frequency distributions. And again, a frequency distribution is how we arrange data according to how frequently various outcomes appear in a data set. So we can show this as a table or as a graph, most commonly as a histogram. So, and that led us to other important things. So you know how to do that, right? So when we do relative frequency, when we do frequency distributions, we look at relative frequencies or percentages and cumulative frequencies. As we go, we add them all up. Here's an example. So here is a age of my sample. So for people 0 to 25, 4 of them my sample. And as I add up the various frequencies up to 100, I get that. Now, if I were to be making a histogram out of this, which column here would I be plotting to create a graph or a histogram of these data? Which one of these numbers would I graph? Interesting, isn't it? Oh, I thought you understood. Maybe you didn't. I'm getting worried now. Yes? The frequency. Yeah, you could graph this one too. That's possible. But most commonly this one. So this is the histogram. And this, I've defined age groups here. I could define the groups differently. We call those, class sizes. It doesn't matter to get various shapes of histograms. Right, so when you look at your normal distribution, that's what that is. It's a plot of this or a plot of that. Right. So like I said, we can have histograms, bar graphs, pie charts, frequency polygons that no one ever uses, but textbook like to talk about it. And that's a distinction between a histogram and a bar graph visually. Remember? Yeah. Exactly. The category is tough touch, and that tells us that in fact we can change the class sizes to have things flow in between them. Right, and here's a frequency polygon. This is the same thing. Okay, we looked at shapes of distributions, modality, symmetry, and kurtosis. What do those things mean? Yes, ma'am? Number of modes, that's right, number of peaks, and next one as well? Yeah? Doesn't have to be a normal distribution, any kind of graph that's the same on a mirror image of each other. And the last one, kurtosis. Peakedness and flatness, correct. Okay, so modality is number of modes, number of peaks. So the cleavage shot or the or the morning happiness shot. There it is. That helps you. Often this leads to that. So then we have, so symmetry, we have positive skew and negative skew. So positive skew is when the tail goes off to the right, and negative skew is when the tail goes off to the left. Again, in a moment of exam stress, you may confuse them because, oh, most of my guys are clustered to the right side. That must be positive. No, it's the other way around. It's the tail that's skewness. So positive skew, negative skew. Okay, kurtosis, remember we have lepto, plata, and meso. And leptokurtic is tall and thin, platokurtic, short and flat, and mesokurtic, somewhere in the middle. And again, we have an index for that as well. Okay. And the jokes here, no, I won't. That's just too good. Okay. You have morning happiness, and morning happiness when you're middle-aged or later. So, okay. So then we looked at measurements of central tendency, how much our data clusters around a particular value. And we said there are 3 measurements that you covered in high school, mode, median, and mean. You know what those are, I assume. And then we looked at how we can measure the width of our data distribution, the variability. So there are 4 different ways of doing that: range, quartile range, standard deviation, variance. And this was the hard one for most people, because that was computing Q1, Q2, Q3, remember that? And what's Q2? Always. It's a median, exactly. And I gave you a formula for figuring out what Q1 and Q3 are. And we define outliers according to what our IQR is as well. All right. So we looked at standard deviation. What's a deviation? Difference between what? From the mean, right? So all it is, we subtract your value from the mean, we square them because we get rid of the minus sign, add them all up, and divide by the total number, we get a standard deviation. And the square of standard deviation is a variance. Okay, and here's how we define our outliers. If it's a mild outlier, then you define it by that number to that of IQRs. And our outlier is greater than that number. We said standard deviation is a measure of deviation scores. Okay, so again, depending upon the level of measurement, this is how you measure your standard tendency, and this is the kind of variation you can use. We tend to rely on this for most of our statistics. Recognize that there's data that has these qualities to it. If I'm analyzing, again, what city you're born in, that's nominal data. I can't do this fancy stuff with nominal data. All I can do is compute how many people came from Toronto, how many people came from Peterborough, how many came from Brockville, that kind of thing. But if I have ordinal data, I can do that, and so forth, which is why we like to have these kinds of variables. They can do more things with them. On the next lecture, we looked at standard deviation. We did that already. We looked a bit at variance already, and we talked about notation. So you got that clear in your head already. This is when it's Greek, parameter. When it's English, it's the statistic. But again, I don't care that much. You know what I mean? So if you get these screwed up, it doesn't really matter. The math is the same. So we look at relative standing a bit. Like I said, we're not doing z-score calculations on the midterm, but I want you to know what they are, right? And to think about them for the theory components. So we looked at percentile ranks and standard scores, which is essentially the number of standard deviations above and below a mean that you happen to be in. We call them z-scores, z-statistics, z-values, normal scores, all these endless things. And we only know this if we know the parameters of a reference population. Because relative to the reference population, how many standard deviations am I away from parameter? Whew, that's a lot of boring stats talk. Damn, I bored myself saying it. Okay, and that's the formula that, well, know the formula. I may not ask you to do anything with it, but know the formula. Okay. You can do that already. So then we introduced what all this means on normal distribution. So if my score is this far from the mean, then it's not common. It's not a typical result. So it's probably uncommon enough that I can say it doesn't fall along the path of wisdom, therefore it's extraordinary, therefore it's probably statistically significant. That's the logic you're reading here. Okay, we looked up z-scores at the back of the book. I'll be asking you to look up things as well on your table. Looked at the 3 sigma rule. It tells me how many standard deviations away from the mean a certain percentage of my data set tends to be. So with 1 standard deviation, we're about 68%. 2 standard deviations are 1.96, 95%. 3 standard deviations, 99%, and so forth. Right, lecture 5 was the fun one on probability. All those fun examples. How to use the Boolean operators of or, and not, and you're all proficient and expert on this now, I know, because I got very few questions about it, so I assume that everyone's cool. We looked at the epidemiology, lecture 6. Yes, ma'am.
But it still said 8 and 9 were difficult, or 9 and 10. Do you notice that?
Really?
The questions were
like the online links.
Oh, right.
Yeah.
Oh, maybe the links changed. Oh, that's odd. So, what's the question?
They were like, I don't know.
Oh, well, if they're no, I mean, if it's really, really hard, that's not. The questions I'm testing are quite simple versions.
Will those be on it? Like, what you have supposed to do, those online questions?
Will I be giving you the questions I gave you already? What's the question?
Those type of questions?
No, it won't be as difficult as it'll be more like the ones we did in the lecture. Yeah. So my logic is I give you the hardest things possible homework so that come exam time it'll be easier. My logic could be flawed. Well, you know, we'll see. Okay. Right. Okay. Okay. So we looked at cohort and case control studies. So what's the difference? Do you remember what the design differences are in a cohort and case control? Yes.
Case control is retrospective and goes back in time, or
Right.
cohort is like current.
That's one distinction. It's not a key distinction, though. What's the key distinction? It's possible that a cohort goes back in time as well. That'll work for you, though. That'll work for you, but strictly speaking, okay, a cohort study is distinctive by the fact that you ascertain exposure status first, and you wait to see what the outcome is. With case control, you ascertain the outcome first, and you look back to see what the exposure was. So here is taking of ARV drugs associated with nausea. So in this guy, find some nauseous and non-nauseous people and check to see if any of them took RVs. So the nausea is the outcome. I've ascertained outcome status first. I'm looking back to see if anybody was exposed to the ARVs. So what design is that? That's the case control, because I ascertained the outcome first. That's the distinction. Okay. So then we looked at 2x2 tables. So remember, when you set up your contingency table, you've got to have the exposure status over here and the outcome status over here. So exposure is the row, outcome is the column. Make sure you've got positive exposure first, and here you've got positive outcome first. If these are swapped, the formulas don't work. So set it up correctly. That's something you can do in your cheat sheet or your reference document. Okay, so this is called a contingency table, and here are all these things we learned about that I'm sure bore you to sleep, but they shouldn't, because these are actually quite interesting. So we have your absolute relative risk, you have relative risk, you have your relative risk reduction, and you have your odds ratio. Which one of these two can we only do in a cohort design? Do you remember that? Okay. Relative risk is only applicable in a cohort design. It does not work in odds ratio. So for case control studies, odds ratios use to estimate relative risks. As an aside, it only works when the disease is rare. But what's rare? 10% or so. So just figure out how to compute those things from your contingency table. There's a faster way to do odds ratio, and that's just these two divided by these two. We'll look briefly at correlations. We're going to more about correlation in the second half of the class. And correlation is like a bond between continuous variables. And we decided that a Spearman's row breakdown is like this. So the coefficient gives you these numbers. We interpret it that way. We decided that closer to 1 is almost perfect linear correlation. Further away from 1 you get more noise, until you get 0, which is randomness. Okay. Then we moved on to types of hypotheses, the null hypothesis and the alternate hypothesis. And remember, the null hypothesis says nothing's going on, or that things are equivalent, which is the same thing as nothing's going on, because we always care about finding differences. If we find no differences, then things are the same. Null, nothing's going on. And we always assume this is the default state, and we seek to reject the null. Do we accept the null? No, you never accept the null. You just fail to reject it. Right, so we write it that way. So we talked about type 1 and type 2 errors. Type 1 error is incorrectly rejecting the null, and type 2 error is incorrectly failing to reject the null. So again, a moment of stress, you're going to get these confused. A moment right now of non-stress for me explaining this orally, I get confused. So for you, it must be impossibly confusing. So try to get these straight in your head. Right? And we call type 1 error by a certain Greek letter. What is that? Alpha, correct. That's very important. Our alpha level is set by the type 1 error, and that also determines our critical cutoff error, whether or not something is statistically significant. So we talked a little bit about directionalities. If we care about whether something is bigger than something else, or if we care if something is smaller than something else, then we care about direction. We do what's called a one-tailed test for that. That means we look at all the possible outcomes of a distribution and only care about what happens on the extreme end of one. If we don't care if it's bigger or smaller, we just care that it's extreme, we do a two-tailed test at both ends of the normal distribution. Then we moved on to the really confusing stuff, the sampling distribution of the mean. Aye, aye, aye. And that's when we had that theoretical concept of if I took a billion random samples from my universe, and I took the mean something from each one, mean age, let's say, and I had to plot the mean age from all those on a frequency distribution, I would get a normal curve. It's magic. That's the central limit theorem. That's what that tells us. And this is a theoretical sample. It's not real because I can't get a billion or infinite number of samples. Okay? From that, I can compute the standard error of the mean, and that is the standard deviation of that magical fantasy distribution. Okay? So we define our, even though that's a fantasy number, we can estimate it using the standard deviation for my sample, the formula for it. And we use that to compute confidence intervals. Remember that? Okay. So all I need to compute that is the mean from my sample and a t-value that I'm looking up that comes from my 95% and the SEM that is computed. In lecture 10, we looked at the standard error of the difference, which is just like the standard error of the mean, except I'm not looking at the means of things. I'm looking at the differences, usually the means of things. So if I'm looking at what two different groups are the same, I will take two samples from the universe, compute the differences, put it away, take no two samples, compute the differences, put it away, and so forth, and then plot this on my magical frequency distribution, and I would get, again, the same normal distribution. And the width of that normal distribution isn't the standard error of the mean anymore, it's the standard error of the difference. Same thing. It's the same idea. It's just a different name for it now. And just like we compute the SEM, we can never really know this, so we estimate it from our own data. Okay? So, then we moved on to t-tests. T-tests is what we use to compute whether or not the means of two things are the same, or whether or not the mean of one thing is the same as an external value. And remember, there are different kinds of t-tests. There's the dependent samples t-test and the independent samples t-test. That's when we have two samples. What's the difference between the two? Independent versus dependent samples t-test. You can answer all the questions, all right?
Independent is when the two samples aren't systematically related to each other?
That is correct.
Independent is
Absolutely correct, right? So dependent is when you're testing yourself, same group twice, or married couples, or so forth. Right, get those straight. So then we looked at how to interpret p-values. And the p-value, again, is where your data exists on that magical distribution, right? And if it's less than my alpha cutoff, then I say I reject my null hypothesis. If the p is low, the null must go. If it's greater, then it's failed to reject it. The null doesn't go. All right. So t-tests are used to compute what? Yes, ma'am? Nope. No. That's too confusing. So SPS computes the p-value for you. When you look up a value in the back of the book, that's what that really is. It's telling you whether or not your p-value from that computation is less than or greater than your alpha. So the act of looking it up on the table is the act of doing this. So that's the old-fashioned format we did before we all had computers. So education hasn't caught up to the fact of all computers. But it's still useful because you get to go through the manual process and figure out what's actually going on. But these days, we just let the computer compute the p-value, and we interpret it. We interpret version relative to our own alpha values. And one day, the computer will do that too. So, right. So t-tests are about comparing what? What measure for comparing? This would be like the first test on the exam. T-tests are what? A, B, C, or D? Shout it out. A, so A. Pulling teeth, you guys. T-tests compare means. We haven't learned how to compare these things yet. Okay? So we can only compute t-tests on data for which you actually can compute a mean. You can't compute a mean on which city you're born in, or you know, how many rooms you have in your house, but it doesn't mean anything. Okay? Can we do this? No, we can't. So t-tests can only be used for interratio data. As I said, we can compare two different samples. We can compare one sample to an external value. And this is probably confusing you more than it helps. But what it's showing is the distribution in one sample versus the distribution in the other sample, and what the difference of the mean is between the two samples. And we're trying to decide, is that difference small or large? Is it so small that we can say they're essentially the same? Or is it so large that we can say they probably came from different universes? It's that universe talk again. That's what a t-test is doing. It's deciding, did the green curve and the blue curve come from the same universe or a different universe? And we decide that by looking at the difference here and saying, is that difference small or large? The sampling error of the difference. That's what we do all that stuff. All right. So the one sample t-test tests whether or not our sample came from a universe in which the mean is a certain value. That's what that tests. Remember, there are a whole lot of formulas for t-tests. Again, I'll only ask you to compute the one for the dependent samples t-test, possibly the one sample t-test, possibly meaning yes. And I won't ask you to compute this one, but I want you to know where it exists in the universe. So there's a cascading process here. So when you get to the dependent samples, you have two other options. Either the variance is the same or the variance is different. How do we decide whether the variance is the same or different? There's another test that SPS runs for us. What is it? Levine's F-test. That's correct. Okay. So an example of a situation requiring a single sample t-test. Well, that's comparing a mean to an external value. Whether or not the mean mark of this class is 50%, because faculty actually cares about these. Is a mean mark of your class, is it low or is it high? Ray, we need your mean mark to 75. Sometimes they say that. No, it's not 75. Go away. Okay. So, or an example of when we require an independent samples t-test. Is the mean mark of this class different from the other stats class? Or an example when we require a dependent samples t-test. Is the mean mark of your midterm different from the mean mark of your final? Have you improved? Have you gotten different? And I will do that at the end of the year. I'll figure out, did you guys get better or worse by running a dependent samples t-test. Okay, the two different types of independent samples t-tests are equal variance or non-equal variances. And we know which one to use by using Levine's F-test. Right, so Levine's F-test, and Levine's F-test has its own null hypothesis. So here's an example. A researcher will determine if plants grow faster in fertilizer 1 versus fertilizer 2. So starting with seeds, he grows plants in general conditions by randomly assigns brand 1 to 7 plants and brand 2 to 6 plants. So in this example, what's my null hypothesis? Yes?
Plants grow the same, both of the fertilizers.
Exactly, right? So equivalence. Okay. Now, for Levine's F-test, what's the null hypothesis going to say? My words. For Levine's F-test, what is the null hypothesis going to be? That's the correct null for actual research question. We need a separate null now for the f-test. This is the same, exactly right. So look at the output now, right? Here, we assume equivariances or equivariances not assumed. Which one do we care about? We care about the p-values here. Care about this. So Levine's s-test is right here. And the p-value for Levine's f-test is 0.79. Is that low or high? That's high. Therefore, do we retain or get rid of the null hypothesis for Levine's f-test? Retain or fail to reject. Okay? So the null hypothesis for Levine's f-test was the variances are the same. We don't get rid of that, so we assume the variances are the same. We look at the first row. And the first row tells me that for the t-test, the p-value is 0.269. Is that low or high? That's high. So what do I do with the null hypothesis for the t-test? Yeah, why not? Because you're in front of me. Say it? No? Somebody say it. Right, so the p-value for the t-test is 0.269, which is high, because over 0.05. So what do I do with the null hypothesis? Fail to reject it. The null hypothesis you said was that the growth rates are the same. Therefore, the growth rates are the same. Okay? One little chart. I look at it right away, I know this. But the process you have to go through is two-stage. First stage, decide which row I'm looking at. Equivariances versus non-equivariances. I decide that by looking over here. And then when I decide which row I'm looking at, I go to value and make my conclusions about the t-test. Yeah? Okay. So again, here's I'm repeating what I just said. Null hypothesis for Levine's f-test was the variances are the same. Right? And that's true. The mean growth rates are the same. Okay. Do we need to run Levine's f-test for a dependent sample as t-test? Usually not. We didn't go into this in detail. We usually have to do so because we're testing the same population several times or systematically related populations. We tend to assume that the variances are the same. So for dependent samples, we don't need it. Okay. The other assumptions for running a two-sample t-test. We assume the cases are randomly selected. Why not? Right? How do we know if they are? How they're designed. We assume that the data must be sampled from a normal distribution. How do we know that? Well, we run a certain kind of test, the Kolmogorov-Smirnov test. And that also has its own null hypothesis. What is the null for the Kolmogorov-Smirnov test? Yes? That there's no issue, exactly. Again, the boring thing is always a null. It's normal, that's great. It's normal, right? And there it is. The Kolmogorov-Smirnov test says 0.2. That's the p-value. We fail to reject, therefore it's normal, because 0.2 is higher than 0.05. Always, when you look at these outputs, ask yourself, which null hypothesis is it testing? Is it testing the null for our big question that we started with, or are they sub-questions like the f-test or the Kolmogorov-Smirnov test? Because again, in the thresh of the exam, you may get that confused. And the last assumption was, well, we can also skip the test of normality if we have more than 4 cases per group, because we assume that that's more than enough, and if you came from a universe where there's normal distribution, then your sample is probably normal as well. And if our groups are somewhat equal size, and the cutoff is usually 1.5 times, not different. Okay. If it's not normal, we didn't really go into this. I don't need you to know how to do this. Know, that they exist, though. Can we do a t-test if you fail the normality test? Not really. We just call it a Mann-Whitney U-test or Wilcoxon-Sum test. You should do that. But most people do a t-test anyway because people suck. You know what they're doing. So, yeah. Will I test you on this? Yeah, why not? Let's say yes, I will. I don't remember if I do or not. So know that if you fail the Kolmogorov-Smirnov test, if you fail the test of normality, the option is one of these two. Okay. In the independent sample t-test, remember, we did the Levine's f-test because we don't know if our samples are equal size. We don't know the variances of the size. We need to run all these different kinds of tests. We run tests to see if the sample sizes are the same. We call that a Welch's t-test. Don't worry about it. Just know it exists. Dependent samples t-test, we also call it a paired samples t-test. In SPSS, I believe it's called a paired sample t-test. We tend to assume the variances are the same because you're testing yourself twice, you're testing husband and wives. So in practice, we don't test for normality, even though we probably should if a sample is just small, but we tend not to. Okay, so testing significance. Remember, we've got 3 different ways of doing it in this class. The first way is we state a null hypothesis. We compute our t-value, look up in the back of the book, and decide whether or not to retain or reject the null hypothesis. We did a lot of that going on, and I'll probably ask you to do that. The other way is we use SPSS to compute a p-value, and you decide is that p-value higher or lower than alpha. So it's kind of the question you asked, how do I get the p-value? Well, in the original method here, back in the book, that automatically expresses a kind of p-value scenario, or we can use a computer to figure out the p-value. And the last way is computing a confidence interval. We only do one of these, not all 3. You can do all 3. What's the point? They give the same answer. So the confidence interval is the preferred method by modern scientists, and that gives me a range in which my result probably fits. And we saw how to do that for means already. Okay, yes? That's for ratios. So remember, whatever we're measuring, the range tells us what the likely value really is. And depending on what you're measuring, that the important number to look for is going to be different. For with ratios, 1 matters for a relative risk or an odds ratio, because if the proportion happening this group is equal to the proportion happening this group, and I divide them, I'll get 1. But for means, not so. Right? What I could do is I can compute the mean age in this group and the mean age in that class over there, compute a confidence interval for this one and a confidence interval for that one, and see if they overlap. If they overlap, then I know that they're essentially the same means. Or if I'm saying the mean grade in this class is equal to or different from 55, let's say. Okay, that's the question. That would be one sample t-test. I can go through this rigmarole doing my one sample t-test calculation, compute the t, look at the back of the book, or I can go to SPSS, p-value, and compare to alpha. Or I can compute a confidence interval for your mean mark, and let's say the confidence interval is, the mean mark is 60, and the confidence interval is 50, 70. So that means somewhere between 50 and 70 is the real answer. So can I conclude that this group probably has a mean mark of 55? Yeah, because 55 falls within that range. So that's, yeah, you kind of, am I confusing you more or adding clarity? Looks on your faces tell me I'm confusing you more. That's where I back away slowly and change topic. Yes?
So in what situation do we look for 1? You said
Ratios only. Any ratio. The word ratio means defining something by itself. Right? Anytime we divide 2 things of the same unit, 1 will tell you equivalence. Right? So if I divide your age by her age, I get 1, the same age. And that's why ratios matter. Okay. Clear? Yeah? Can we go over more? Good. Okay. So when you look up stuff in the back of the book or the tables, you need to know degrees of freedom. One of those ridiculous stats terms that I hate, we're stuck with it. And degrees of freedom really is a proxy measurement for the number of people in your sample. And there are different ways of expressing the number of people in your sample. For one sample, it's t-test, remember, it's n-1. For 2 samples, it's everybody minus 2. For dependent, number of pairs minus 1. For ANOVA, it got more complicated, but we're not doing ANOVA for the midterm, so don't worry about that. You have to know your alpha level. Unless I tell you otherwise, it's 0.05, sometimes 0.01. You need this to look up in the back of the book. You need to know whether it's a 2-tailed or 1-tailed test. In this class, it's always going to be a 2-tailed test for t-tests. But I want you to know that 1-tailed tests exist and why they exist. Okay, so when you look up the back of the book any kind of statistic, whether it's a t statistic or a z statistic or an f statistic, for example, it'll be t statistics, you want to know if your number is bigger than the book's number. If your number is bigger than the book's number, then we reject null. Okay, we want that. We always want to reject the null. That's not true. We don't always want to reject the null. It's exciting to reject null. That's what we want to reject the null. We found something. So if your number is big, we can reject the null. If it's not, we fail to reject the null. So get that clear. As long as people get that confused, again, in the stress of an exam scenario. Okay, here's some examples. In a t-test situation, confidence intervals are conducted around which one? Which of these computations would I build a confidence interval around? So here's a scenario. If I'm trying to figure out is the mean age of this class different from the mean age of that class, and I do one computation to figure this out, what do I do it on? I'm getting worried. Take a guess. Let's go through the list. Is it going to be the different variances? No. Is it going to be the pool variance? No. That leaves these two, obviously, and you're struggling with which one it is. Now, technically, I could do both of them. They both kind of work. Like I said, I can compute the mean of this group and build a confidence interval around it, and the mean of that group and build a confidence interval around it, and I can see if they overlap. But I said I'm doing one computation. The one computation is the difference. So with the confidence intervals for t-test, we look at the difference between the two means. S-test output also gives you the difference. Remember the standard error of the difference, that measurement? That's what you use to compute a confidence interval for t-test. You take the difference between the means that you compute and the plus minus of the t-value times standard error of the difference. Okay. All right. Yes? Yeah, I mean, I've not taught you how to do two computations about this. So it is possible for you to figure out mean age of this group plus or minus a certain error. So I take the mean age of this group and I get plus or minus a t-value multiplied by, or a z-value multiplied by the standard deviation. That would give me an error bar for a different group. I can do that. That's not what we did, though. We did the t-test scenario, which is when we took the difference to two means. I kind of regret now introducing this idea, because now I realize I didn't teach you that, but I thought it was fairly intuitive. So with t-test scenario, what we're doing really is measuring the differences between the means. Like when I showed you those two curves that overlap, I said we care about the difference. Whether or not that difference come small or big, it came from a universal which is small versus big. That's what we're doing here. We care about the differences between means and how big or small that difference is. And the confidence interval tells us how big or small it is. If it's small, then it's quite likely I can end up finding something significant. Okay. Next example. In this data set, what is the mode? 10, 11, 12, it's a giveaway. Obviously, it's 15. Common number is 15. The mode is going to be D. And yeah, you got some questions like that too. Okay, which of the following is a continuous variable? Number of times married. Is that continuous? Age of first sexual experience? Maybe. Car crashes last year? Number of pages in the book? Which one is continuous? Is the first one continuous? Really? Tough one, because technically, I'd say they're all continuous. Now, the textbook would say not. The textbook would say this would be an ordinal variable. It is an ordinal. I would say ordinals are kind of continuous. Age of first sex experience? Absolutely, because you can be 14.75 in Kentucky. I'm going to assume you're older here. Crashes? Well, you can't have 1.5 car crashes, so that would be an ordinal number as well. Number of pages also. So these three, A, C, and D are ordinal, and B would be a ratio level. Now, it depends what your definition of continuous is. So I wouldn't be so ambiguous to call this continuous. I would say the following is a ratio measure. Because some people would say they're all continuous. So not to confuse you, but that's the difference there. So this is a question taken directly from the textbook's data bank. And what they mean is continuous is just that, and they count ordinal as continuous. Okay, that's all. You looked at us now, yeah? Okay, cool. All right, I'm sure I'll get a lot of emails with him now. And TA will set up a special session for she gets back. I will be out of the country next week, so we'll do that. Okay.